Bismillahirrahmanirrahim. In this video, we will discuss about diode and how to solve diode circuitry in AC analysis. At first, we need to know what is the diode AC equivalent. If we refer to the previous lecture, we need to substitute the diode with its DC equivalent model. We have three types, right? First is the ideal model, second is the piecewise linear model 1, and the third one is piecewise linear number 2. And why we need to do that, the equivalent model, because we don't want to use the iteration methods, because iteration method is try and error, so you need to do a long calculation just to find ID and VD. Let's consider a circuit that has two input source. First is the AC source and the DC source. So hence the total input voltage coming into the circuit has the DC component and also the AC component, and hence the ID, or the current that flows in this circuit, okay, will have ID here. Okay, we'll have the IDQ DC component and ID, which is from the AC component. The same as the VD, okay, voltage across the diode, we will have the DC component and AC component, where the IDQ and the VDQ are the DC, quiescent diode current and voltage respectively. So what does a quiescent point or Qpoint means? So Qpoint, or the operating point of a device, is also known as a bias point. So it is a steady state DC voltage, or it's either current, okay, or voltage, okay, at the specific terminal of an active device such as diode or transistor with no input supply, input signal applied. Okay, so if we look at this graph, this is the current ID current curve. So let's say we already found out that the Q point is here, in the Q point or the biasing point is here. Okay, so we need to find the slope here, and the value of the slope will be GD here. Okay, it is equal to 1 over RD, and from there we can see that if we extrapolate this line, the IDQ value is here, right? So IDQ will be the reference or the locus point for the AC to operate, and the AC value, if we superimpose the AC value, we will see that the Q point will allow this signal to be operating without any saturation. The Q point or the bias point is used for a device like diode. Okay, means that we want the diode to operate at a steady DC input, and it means that at that point the diode can operate correctly without saturation when performing its role. Okay, for example, if we have here the current value is from 0 to 10 milliampere, for example. So let's say that the IDQ is 5. Here is 5 milliampere. So when we superimpose the ID AC signal of the AC signal, okay, it can operate without being saturated at both sides. This is the negative side and this is the positive side of the ID, and it means that the waveform is perfect without any clipping or any cut off or saturation. Okay, and similarly, if we look at this Qpoint for VDQ, okay, the VD signal, okay, superimpose as at the VDQ as the reference, okay, it can have it must have it allows the waveform to be operating at both sides without saturation. Now let's discuss how we come about with the AC equivalent diode circuit. Okay, so if we look at this circuit, we know that the total current will have the DC component and AC component, and if we rewrite the equation, ID equation, as diode ideal current, so we will use this IS formula, right? IS multiply with the whole bracket consists of exponential VD, or this is the total voltage, over VT. VT is the thermal voltage minus 1, and this can be approximate as these two terms. Okay, first is the term with the DC value, and this is the term with AC value, and from there we can say that the IDQ, okay, IDQ is equivalent to IS exponential VDQ over VT. So the VDQ is the Qpoint for voltage, Qpoint, and VT is the thermal voltage. And if the VD value is very less than the thermal voltage, the equation of this AC component, okay, can be expanded into a linear series as 1 plus VD over VT. Therefore, the diode current voltage relationship can be represented as, okay, so the DC with a term that has the DC component and the AC component as well. Okay, so therefore we can say that total ID will have this DC IDQ DC component and ID of the AC component, okay, where this ID is from this equation. Alright, so the relationship between AC component and the diode voltage and diode current is like this. Okay, so we can rewrite ID as IDQ over VT multiply with VD, and IDQ over VT, this is actually GD, right? And then VD is actually VT over IDQ multiply with ID, and this is equal to RD ID. Okay, hence we can say that RD is equivalent to 1 over GD, or it is equivalent to VT over IDQ. So if you are required to find the RD value, you need to know this formula, VT over IDQ, or if given the transconductance, which is GD, so it is the 1 over GD. Hence, this is the diode equivalent resistor. And what does it mean? If we refer to the DC equivalent, we need to change the diode as battery for VDQ is equal to V gamma. This is piecewise linear 1, model 1. And for AC equivalent, we're going to change the diode as RD. Okay, so we substitute, when you see the diode in the circuit, to solve in AC analysis, we need to change the diode into RD. I think that's all for today. Thank you.